Hello everyone and welcome to Module 10. In Module 10 we'll be talking about regression analyses. We'll talk in this module about bivariate or simple linear regressions. We'll also talk about multivariate or multiple linear regressions. In Module 11, when we cover nonparametric statistical techniques, we'll talk about logistic regression, which is a variation on regression analysis in which the outcome variable is not normally distributed, and it's not normally distributed because it's a dichotomous outcome in a binary logistic regression. So for right now, let's focus on linear regressions, and we'll talk about simple linear regressions and multiple or multivariate linear regressions. The basic logic of regression is, in a lot of ways, an extension of correlation analyses. Regression is synonymous in this case with prediction, and regression is an application of correlation to be able to make predictions. And so what regression analyses do is they compare the predictive model that we create to the actual data that we have collected. And regression analyses will allow us to develop a model that will help us predict the values that we're interested in predicting. And it will also tell us how well we did with that. So compared to our actual data, how good of a job did we do in creating a model that best predicts what we see in the world. And so in simple linear regression, we'll talk about having one predictor variable and one dependent variable or outcome variable. And we'll also talk about multiple or multivariate linear regression in which we have more than one predictor variable. So some examples of research questions that could be answered using linear regression are things like, does substance use predict the frequency of sexual risk behavior? I think I mentioned in one of the Google Hangouts that we'll talk a little bit more in the nonparametric module in Module 11 about count variables, which would be the number of risk behaviors, the number of acts, things like that. So we'll talk about some variations on some of these techniques for non-normal distributions, which count variables often are. But for now, let's disregard that. So substance use predicting the frequency of sexual risk behavior would be a kind of question that we could answer using regression analyses. Does sensation seeking predict the frequency of sexual risk behavior? We could answer that with regression analyses. Do internalized homonegativity and sexual compulsivity predict someone's internal conflict about condom use? This is one that we'll come back to. This is the research question for the Module 10 assignment. In the example that we'll go over, perhaps not surprising to you at this point in the semester, we'll be looking at contraceptive self-efficacy as our outcome variable, and we could ask a question such as, do self-esteem and gender predict contraceptive self-efficacy? So we'll go through this example using the AdHealth data as we do every week. So we're going to talk a little bit about the math behind the regression. In some of the techniques that we've talked about, I haven't spent a ton of time talking about the formula. Your book does give a nice overview of some of the basic underlying calculations behind many of these statistical techniques. And so I'll talk a little bit more about this one because this equation is actually important. Some of the output that we get will make a little bit more sense to you, I hope, once you have a sense of what this formula looks like. So a regression equation is a formula for a straight line, basically. So if you think way back to some of your algebra classes, you might be able to think about what that formula looks like. So this regression line or this regression equation, regression line equation is one in which it produces a line that minimizes the sum of the squared deviations between the actual scores people have on the outcome variable and their predicted values on that outcome variable. So essentially, we want to create a regression line, and we talked a little bit about the regression line in the correlation lecture. We want to create a regression line that best predicts everyone's values. And so we want to minimize the distance between people's actual values and the values that we would predict according to our regression line equation. So you'll see a couple variations of this equation. Your book gives this one, and so I'll stay consistent with the Salkind text. This is y prime. Sometimes you'll also see this with a little hat over it, just a little upside down v. over the top of it, and you'll hear it called y hat. For us, we'll stick with y prime, and so y prime equals bx plus a. So y prime is the predicted value on the outcome variable. That's what we want to try and get. A is the y-intercept, or the point where the regression line crosses the y-axis. In a sense, this is the value of y when x is at 0. The b value here is the slope of the regression line, which is the amount of change in the predicted values of y for a 1 unit difference or change in the value of x. And I'll show you a picture of this in just a second. And x is just x. It's the value of x, or our predictor variable. You may also see this written as y equals mx plus b. This is sort of the basic algebraic formula for a straight line. And in this case, m is the slope and b is the intercept, so it's a little different. You may also see y equals a plus bx, which is just the formula flipped around a little bit. A is still the intercept and b is still the slope. And we'll also talk in a second about the variation of this formula when we have a multiple regression or multivariate regression. So this is the formula for a simple linear regression. Y prime equals bx plus a. So this is a little bit of a graphic of what this looks like. And so if we think about this basic, as we've been looking in SPSS, the basic scatter plot, if we think about all these values that would be scattered over here, such that every case is where somebody's score is on both x and y. And so in this situation, the y-intercept over here is where people fall on this y variable, this outcome variable, when x is 0. And the slope is essentially the change in that y variable over the change in the x variable. You'll sometimes hear this called rise over run. And essentially what this means is for every unit increase in x, for every jump in score in x, how much does y go up or down? How much does y change? And so this delta symbol here represents change. So this basically says the change in x over so the change in y. So the slope is the change in y divided by the change in x. There are a lot of different formulas that help you get to the slope. I'm not going to talk a ton about those. These are associated with the correlation values. And so this is the slope is the way in which correlation is similar in a lot of ways to regression analyses. And so I won't spend a ton of time talking about how to get the y-intercept or how to get the slope, but the basic formula for the regression line upon which this entire equation and statistical test are based does depend on this slope and this intercept. So this line that we're trying to fit to our data is a line that we try and use to best represent the pattern that we're seeing in our actual data. And so by trying to find a line that best represents what we actually see in the data, that will help us moving forward to be able to say, based on what we know about these typical associations, how can we use this equation to be able to predict people's scores moving forward in different samples in the population? So this is an equation that will help us to predict people's scores outside of our individual sample of people. So multiple regression or multivariate linear regression is the same thing, but it's a regression that includes multiple predictor variables. And in this situation, predictors can actually be continuous, so these interval or ratio variables, or they can be dichotomous variables. So for example, gender or biological sex, in which we only have 2 levels of that variable, male or female. This could be a variable that is race or ethnicity, if we were to dichotomize people into white and people of color. You may also read in some textbooks, and I don't think this textbook talks about it, the Salkind textbook talks about it, but you can read about dummy coding variables. And that would be a situation in which you could take a single independent variable that has more than 2 levels and change that into multiple independent variables, each with only 2 levels. So you would essentially, let's say we had a race and ethnicity variable that had 4 or 5 different categories. We could turn that into multiple independent variables, each with only 2 categories, and use those as multiple independent predictors in a regression model. So we won't get into that in this class, but I do want you to know that that's an option to be able to include variables, categorical predictor variables in your regression that are not necessarily dichotomous already. Each predictor should be correlated with the outcome variable, with the dependent variable, but ideally they should be minimally correlated with one another. I believe I talked about this in the data cleaning and screening lecture that I gave towards the beginning of the semester when we talked about multicollinearity. And the conceptual reason behind this is, let's say you have 2 different variables, and it turns out that they're actually measuring essentially the same thing. So they're very, very highly correlated with one another. And putting both of those variables in the model to try and predict an outcome variable just doesn't make sense. They're both going to capture the same amount of shared variance if they're measuring essentially the same thing, or if they're highly associated with one another. Typically, the independent variables that we include, if we include multiple independent variables, are somewhat associated with one another, but what we want to do is make sure that those aren't highly correlated with one another. And so the formula in a multiple regression changes a little bit. Here we still have this basic y prime equals bx plus a, but we just have this association, this multiplicative term here, so the slope multiplied by the individual x variable for each of our predictors in here. So in this case, I'm showing you 2. If you have 3 predictors in here, it will be bx1, bx2, bx3 plus a. So this could go on depending on the number of predictors you put into your equation. And so you can put these predictors into your model, and often when we're talking about a model, we're talking about the full model here. So all the variables that we have in here in this full model or equation and what we're trying to predict. So we could put our different predictor variables into the model in a few different ways. Most people, you'll see them do them simultaneously or hierarchically or blockwise. And so you can decide on the order of entering which variables go in first and which variables go in on a second step. Those decisions are usually done fairly theoretically or conceptually. So you may want to say, I want to look at the role of gender in predicting this outcome variable, and then I want to add in a second variable and see if that does much better than just including gender in the model, for example. So you would have some sort of theoretical reason why you think that they should be entered on different steps, or why you should think that they would be entered stepwise or backwards, in which case you include a predictor, and then there's a model test that happens to decide which predictors are least useful, and it will kick those out. So these are very theoretically informed. For most of what you're going to do, you're probably going to be looking at either simultaneous entry or what's called just enter in the model, and I'll show you what that looks like in SPSS, or hierarchical entry, in which you decide on some particular order of entering. So I won't spend too much time talking about those. In the examples that I'll give, we'll enter everything simultaneously. As with all of our analyses, regression comes with a variety of assumptions. These are largely what we have already gone over before, so I won't spend a ton of time on these. In regression, we want to have a continuous dependent variable, ideally one that is fairly normally distributed or would be normally distributed in the population. We want to have linear associations between our continuous independent variables and our dependent variables, similar to what we talked about in correlation analyses in Module 9. We want to have minimal association or correlation between our independent variables in a multiple regression. So when we're including multiple independent variables, as I said before, we want to know that those are minimally associated with one another, so that we're not putting in variables that are essentially the same thing. We want to have normally distributed independent continuous variables. So for those variables those predictor variables that are continuous, we'd like for those to be as close to normally distributed as possible. We want to have homogeneity of variance, so this is the same idea as in the correlation analyses, where we want there to be the same level of variance, or the same amount of variance in one variable at every level of the other variable. So this is that scatter plot that we looked at last time, to be able to see how those variables related to one another, and to try and assure ourselves that the variance was the same at all levels. And I think we talked about this in correlation as well, but we always want to watch for outliers because we're looking at these linear associations between two variables or two or more variables. These outliers can have a strong influence on our values. So we want to make sure that there aren't people in there who are unduly influencing the results that we get. So let's talk about this four-step process of conducting and interpreting regression analyses. So we want to state the null and alternative. In this case, we often talk about the beta values or the b values, and essentially what this is saying is that the slope is 0, that there's no change in y over x, or that there is a change here. In the example that I'll show you, I'll talk about null and alternative hypotheses for each of the betas, and also for the full model to give you a sense of what that looks like and the sort of different levels of things that we're talking about in regression analyses. As always, we want to make sure we meet the test assumptions. We want to calculate the test statistic and once again be grateful for SPSS and that we are not calculating all of this by hand. And then we'll make a decision and interpret the results. So just a quick recap, I just gave you the same information, but these assumptions are that we have a continuous dependent variable that's roughly normally distributed, that there are linear associations between our continuous independent variables and dependent variables, that there is a minimal correlation between independent variables if we're using multiple regression, that we have normally distributed or roughly normally distributed independent continuous variables, homogeneity of variance, and again, we want to watch out for those outliers. So we use SPSS, and we make the decision based on several p-values, actually. And then we want to look at the strength of that prediction or association and the direction of the prediction or association. We want to look at how good the full model does at predicting our outcome variable. This is particularly true when we have multiple regression happening and we have multiple independent variables in the model. And then, as always, we want to think about the clinical and practical significance. So let's go into regression in SPSS and run through a full example. All right, so let's continue and go through and do a full example in here in SPSS. So we're going to stick with the same kind of research question that we have looked at before using the AdHealth data set. So in this situation, we're going to include two independent variables. And when I run through the example, I'll show you what it would look like with just the single independent variable, and I'll then put both in there just to give you a sense of what that looks like in both situations. So for this research question, let's ask, do gender and self-esteem predict contraceptive self-efficacy? So these are both associations that we've looked at before, independent of one another. We've looked at gender and done a t-test to examine the difference in levels of contraceptive self-efficacy. We've looked at the correlation between self-esteem and contraceptive self-efficacy. And now we want to be able to predict contraceptive self-efficacy scores. So we want to be able to say, all right, knowing what we do about adolescents and young adults, can I use these two variables to be able to predict contraceptive self-efficacy scores, to be able to better understand and predict how confident young people will be in their ability to use contraception effectively in the face of factors that would make it more challenging. So our null hypotheses, we can talk about this full model. This is an F value that we get for the full model. So we could say our full model does not account for a significant amount of the variation in contraceptive self-efficacy. and our slope for the first factor is 0, so gender does not predict contraceptive self-efficacy. Our slope for the second factor is 0, that self-esteem does not predict contraceptive self-efficacy. Our alternative hypotheses are that the full model, the variance it accounts for is not 0. It's greater than 0, typically, is what we're thinking here. The full model does account for a significant amount of the variation in contraceptive self-efficacy. And that our first factor, the slope is not 0. In this situation, we would say greater than 0, the absolute value of 0. Gender does significantly predict contraceptive self-efficacy, and self-esteem does significantly predict contraceptive self-efficacy. So we'll check that our assumptions are met. We've done all of these already. The levels of measurement are good. We have continuous variable for the outcome variable and for our independent variable. One of those is a dichotomous independent variable. So we're fine on both of our independent variables and our dependent variable. We have minimal association between the independent variables. This is what we looked at in the correlation analyses in Module 9. And what we found was that there is a significant association, but it's a pretty small one. So we're not going to worry about it in this situation. But we did also determine that there is a linear relationship between that continuous independent variable of self-esteem and our continuous outcome variable of contraceptive self-efficacy. There won't be a linear relationship between gender and contraceptive self-efficacy because it's a dichotomous variable. We don't think about linearity in the same way as we do with continuous variables. We do have, it seems, homogeneity of variance between our continuous independent variable and our continuous outcome variable. And we also looked at the homogeneity of variance in the t-test when we very first looked at gender and its association with contraceptive self-efficacy. So we'll go ahead and say that those are essentially good enough, and we'll move forward. And we looked at the distribution of all of these variables. They're not perfect, but we have a really large sample here, so we're not going to worry about it. So we don't have gross violations of any of our assumptions. So we're going to say good enough, and we're going to move forward. As we talked about, I think in the correlation analysis, we don't really have outliers on either of these variables because they are scale scores on a particular measure. They are bounded, so people can't get any higher than a certain score on either of these variables, on self-esteem or contraceptive self-efficacy. And so we're not really going to have outliers on these particular kinds of variables. Outliers often happen more often with count variables. So for example, the number of sexual partners or the number of sexual acts that people have. I think I might have given this example. I don't remember if I did it in a lecture or in a Google Hangout. In a data set that I'm working with a lot, we have number of sex acts, vaginal or anal sex acts, in a 2-month period or a 1-month period, I forget. And most people have like, I think the mean is like 7, 8 acts in a month, I think it is. And then we have a couple of people in the sample who, I don't know how they have the time for this, but one guy has, I think, 140 acts in a month, and another one has like 107 acts in a month. So they exert a lot of influence on many of the analyses that we run. So we're constantly making decisions about whether or not to kick those two out of our analyses because they are so different than the rest of the sample and really screwing everything up with all their sex. So in this situation though, because we're talking about variables that are bounded by the nature of what they are, we're not worried so much about the outliers in this situation. So we're going to conduct the test. I'm going to switch over now to SPSS and show you what that looks like. So we'll come over here. I'll say a couple of things really quickly before we get started. So I talked a little bit about this on Google Hangouts in one of our recent meetings. So when we select the data, I've shown you guys how to kick people out of the analyses basically. And so in this situation, we have some people with missing data. If you click on any of these columns when you're in data view and you right click, you can always sort ascending or sort descending. So let's sort ascending. And this basically puts all these missing people up front. And so if you remember when we calculated this contraceptive self-efficacy score, we only get contraceptive self-efficacy for people, excuse me, who are interested in using birth control. So if they said, I think 6 was the response that they could give if they said, I don't want to use birth control at all, in which case we don't want to know how confident they are that they could use birth control. And we're only asking this to people who I think have had any sexual activity. I think that's the caveat for this particular variable. So we have a bunch of people here who are missing. There are 1,111 people who have missing data on this. We can do the same thing over here and sort ascending. We only have 12 people who are missing here. And the nice thing about regression analyses and correlation analyses is that those analyses will only run on people who have both of these variables. So correlation will only run on people who have both of these variables. The trick, and something that I wasn't worried about with correlation, so don't freak out that you did it wrong, is that when we get the mean and standard deviation for each of these variables, for example, self-esteem is going to give us the mean and standard deviation, and it's going to include all of these people. So the regression analysis and the correlation analysis will only include them if they have both values, but when we run just the basic simple mean and standard deviation, it's going to catch those people in there and give us a mean that might be a little bit different than the mean that is of the people who we included in our analysis. So we can do a couple of things to get rid of these people. We can just straight up delete them. So in this situation, we can just select all of these people. We can come over here and right click and clear them out. Because you can download this data set again if you accidentally screw it up, or delete people that you didn't mean to delete, or deleted them and then have to run some other analysis later where you want them back in there. You don't have to worry about it, but we can also go up here and do data, select cases. This is what we did. And so I've already done this in here, but I'll show you how to do it. So what I essentially have in here is that I want to make sure both of these variables have data. So let's actually just reset this and I'll show you. So we want to click if condition is satisfied and then tell it what if. So in this situation, I want to say, I want to make sure self-esteem is greater than 0. And I want to make sure the contraceptive self-efficacy is greater than 0. So I'll tell it continue. It does not, like that, because I didn't put actually the contraceptive self-efficacy score in there. So now I can tell it the contraceptive self-efficacy is greater than 0, and it should like that. And so in this situation, I've already done this, so I won't run it again. But this is essentially what you get in this situation. So it's gotten rid of everybody who has missing data over here on contraceptive self-efficacy. So there are some people who have data on self-esteem, but it's getting rid of those for us. And there's a few people here, I think, who have data on contraceptive self-efficacy but don't have data on self-esteem. So it's getting rid of all those missing cases for us. So now when we go to do the basic mean and standard deviation of each of these, we do our statistics and we'll get our mean, median, our mode, our minimum, maximum. We can get our skewness and kurtosis. We can do our histograms on here and get a look at the normality of these variables. When I do this now, it's only going to give me the people who will be included in this ultimate analysis. So this 3719 should look familiar to you because it's the number that you got when you ran your correlation. So what we see here is a mean, median, and mode for each of these variables, only including those people who have data for both of these. So you can look here and get a sense of how these look. For both of these, we decided that they're not perfectly normal, but they're also not terrible. We can look again at the mean, median, and mode and see how close they are. So for self-esteem, they're actually pretty close. It's not too bad. Contraceptive self-efficacy, the mode is a little bit off, but again, not terrible. So we're going to go ahead and keep that. Both of these are a little bit skewed as well. And I explained this in the Google Hangout recently, but I want to say it again. the percentages that we get, this percentage column here will give you the percentages including the people who are missing. We can't see it in here because we got rid of all those people. Typically when we're reporting percentages, we want to report the valid percent because that will give us the valid percent of the people who have actual data. And so we'll just ignore all the missing people who would be over here if we hadn't kicked them out already. And so typically when you're reporting percentages, you'll report a valid percent. And so we'll also go over here and get this information for gender. And for gender, we don't have to put anything, so we just want the frequency table, which is typically the basic default here. So we'll get this information. There's no missing data for the biological sex variable in here. But what this tells us is that 48.5% of the sample are male, 51.5% of the sample are female. So, so you report if you have dichotomous variables, you report the percentage when you report the basic sample characteristics or the scale characteristics. And when you have these continuous variables, you report the mean and standard deviation, as well as the range, the minimum and the maximum for each of these. So that's a couple of things. I won't show you the histograms again. We talked about that in correlation analyses, but you could run that histogram again, that same one that we did, if you wanted to look again at that linearity and the homogeneity of variance. But for now, what we're going to do is we're just going to look at this regression analysis. So we want to go to Analyze, Regression. We're going to go to Linear. You see that there's a whole lot of options here. We're going to talk about linear, and then in Module 11, we're going to talk about binary logistic regressions. So for right now, let's talk about linear. I'm going to reset everything just to show you how I do this. So in our dependent variable, we're putting contraceptive self-efficacy in here. In our independent variable, we're putting in self-esteem and this biological sex variable. These blocks here, this is when you want to enter things hierarchically. So let's say, for example, I wanted to put in gender, and then I wanted to do a second block where I put in self-esteem. That's how you would do that. And then you could choose this method if you wanted to do stepwise, backwards or forwards removal. That's how we would do that. So for right now, we're going to go ahead and keep everything in just this one block. So we have self-esteem and biological sex in there. We have contraceptive self-efficacy as our outcome variable. Under statistics, we don't really have to check anything else. We could put descriptives. If we were doing a hierarchical or block entry method, we would want to look at the R-squared change. What that would tell us is when on the step that we added another variable or another set of variables, how much more variance are we explaining by adding that variable or set of variables. We could also get confidence intervals, which I think is nice to look at. And so let's just do that. We don't have to do anything else. Another way to check the homogeneity of variance assumption would be to plot the residuals. We're not going to do that in this situation. So we're just going to look at a pretty basic analysis here. You don't even have to put in confidence intervals or descriptives if you don't want to. You can just leave all of the basic default options as they are. You can hit paste and run that syntax. For now, we'll just hit OK. All right, so it does give us these descriptive statistics up here. So this would be a way to get those stats without having to remove all those people. And so what we'll see here is some basic correlation. So this should look very similar to you. This is this correlation value that we found in Module 9 when we looked at the basic association between contraceptive self-efficacy and self-esteem scores. This tells us essentially what variables are in the model and how we entered them all at once in this enter method. And then we'll look at these three sets of output. So this first one is our model summary. And the things that we're looking for here, the main thing we're looking for here is this adjusted R-squared. And I always recommend using the adjusted R-square that accounts for the number of variables that you have in the model and gives us a sense of a population level adjusted R-squared. And so what this tells us, as with the R-squared that we did for the correlation analysis, and as with any effect sizes, it gives us a sense of how much variability in our outcome variable can be explained. And in this situation, because we have multiple predictor variables, this tells us how much variability in contraceptive self-efficacy is explained by all the variables in the model. So what we see here is 7% of the variability in contraceptive self-efficacy can be explained by both gender and self-esteem together. And then we want to look at our ANOVA. So the main thing we want to look at is the significance value over here. And so that basically tells us whether or not this is a significant amount of variability that we're explaining in contraceptive self-efficacy scores. If this is not significant, we typically stop right there. We don't go down here and look at the coefficients. If we don't have a significant overall model, we're done. And so what we see here is that we do have a highly significant model, so P is less than 0.001. We don't know exactly what it is because that's much smaller than that. So we would say P is less than 0.001. This is a standard ANOVA table. So we have our degrees of freedom here, which is 2 and 37/16. And we'll report this F value right here. So this is our overall model. So thinking about having both of these predictor variables, self-esteem and biological sex, in the model, are we accounting for a significant amount of variation or variability in contraceptive self-efficacy? And so what this is saying is we're accounting for significantly more than 0. And so those are the basic overall model statistics that we're looking at in the model summary for the adjusted R-squared and the overall ANOVA. And so this is typically what you want to look at first. If we have a non-significant F value, then the whole thing is pretty much done at that point. So in this situation, we have a significant model. So you want to come down here and look at these predictors and see what's what in terms of how significant each of these predictors are. So our constant here is essentially our A, if we think back to the regression equation that we talked about before. So this is essentially our y-intercept. And so we're typically not interpreting this. There are situations in which we do want to interpret that and think about what that means and how our values are coded. For now, we're going to ignore that and not think about that. And so we're typically ignoring really that whole line. What we are interested in are these 2 rows for each of our predictor variables. So this is biological sex, and this is our self-esteem score. And so what we see here, these are the slopes. These are unstandardized values, which means that we can interpret them according to the actual scale that our dependent variable is on. And so what this is telling us is for self-esteem, let's talk about that one first. So for every 1 point increase in self-esteem, contraceptive self-efficacy goes up 0.137 points. So that tells us that there's a positive relationship here between contraceptive self-efficacy and self-esteem. We know that that is a significant relationship. P is less than 0.001. And I'll come back in just a second to the standardized betas. We have biological sex here, which is a dichotomous variable. So this is a little bit different in terms of how we think about interpreting it, although because those values are coded 1, 2, we can think about this in sort of a sort of pretty standard numerical way. So in this situation, males are 1, females are 2. So we can say that the higher the value in biological sex, so that would be females because they are the higher value, the lower the levels, this is a negative value here, the lower the levels of contraceptive self-efficacy. So for every 1 point increase in biological sex, which there is only that 1 point increase, there is a reduction in contraceptive self-efficacy of 0.982. And so the standardized values, what those do is give us these slopes, putting them on the same scale. So they allow us to compare these 2 values in a way that these don't. Because these scales are different for self-esteem and for biological sex, we can't necessarily look at these two and say, oh, this is a stronger effect than this one. We don't necessarily know that because those are measured on different scales. But when we come over here, we can compare these betas and see which one is stronger. There are tests that you can do to figure out which effect is stronger. In this situation, we're not, but this allows us to look at both of these effects on the same scale in a standardized way. And we'll typically report both of these when we talk about these. So in this situation, what we find is that our overall model is significant, that each of our predictors are significant predictors of contraceptive self-efficacy, and we know how strong those predictions are based on these numbers, and we can interpret sort of what that means for the increase in contraceptive self-efficacy scores when each of these increase, and we also know the direction. This variable is a little bit confusing in this data set because, as we've talked about before, higher levels of contraceptive self-efficacy indicate that you actually have lower levels of self-efficacy, and the same thing for self-esteem. I can show you maybe at some point how to think about reverse coding things to make that make more sense. I always like to have my variables be a little bit more intuitive than that, such that higher scores would mean more of the construct or higher levels of the construct. I think that's just easier to think about and not have to flip things in your head multiple times. But for this, we actually have to think about this in terms of what these constructs mean. So I think that's particularly challenging to think about with biological sex to think about. So what we know is that females then have lower levels of contraceptive self-efficacy, which actually means that they have higher contraceptive self-efficacy. So that is consistent with what we found in our regular t-test. So that is a multiple linear regression. And if we come back here to the PowerPoint, these are the values that I was indicating to you. This is how you would write out that overall model. And these are the places that you would look. I just wanted to have this in the PowerPoint so I could draw your attention to those places. So then we would make a decision and interpret our results. So this is our F value for the full model. So we would reject our null hypothesis for the full model. These are our betas, our slope and our betas for self-esteem and for gender. So we would reject the null hypothesis for each of those individual betas. And this is how we would say this. So we conducted a multivariate linear regression wherein self-esteem and gender were entered simultaneously as predictors of contraceptive self-efficacy scores. The model was significant, and again, what that's telling us is that the model as a whole predicted a significant amount of variability in our outcome variable. Self-esteem scores contributed significantly to the prediction of contraceptive self-efficacy, as did gender. And so we have our basic slope in here, we have the standard error of the slope, we have our beta value, so again, this allows us to look at these in a standardized way, and we have our p-values in here. The model accounted for 7% of the variance in contraceptive self-efficacy scores. So for your actual assignment, I am planning not to write up a full version of how I would write up this assignment, but let me know if you feel like that would be really helpful to you to see that, or if you feel like after seeing a couple of those, you have a better sense of what those write-ups look like. So what I'll actually do now is go back to SPSS and show you what this would look like if we were only to include one variable in the model. So if we wanted to go up here and go to regression and linear regression, let's say we're not interested in gender here. We only want to know about the self-esteem score. So we could get rid of gender and just say we're using one variable, one independent variable to predict our one dependent variable. So we could run that. And so what we would see here is we see in this model summary our adjusted R value. We want to always look to this ANOVA table first, and this is a significant model overall. We're down to 1 degree of freedom here because we only have one estimate that we're making here. And so we do have a significant model. The full model accounts for 3.1% of the variability. So self-esteem alone accounts for 3% of the variability in contraceptive self-efficacy scores. And if you look here, this is the exact, so 0.176. And if we look up in this correlation table, 0.176. So this is exactly what we got when we did the basic correlation here. So this is same when we have only that one predictor variable in here. And so when we come down here, we can look at this self-esteem score and look at the coefficients. So our standardized coefficient here, the slope is 0.122. So for every 1 point increase in self-esteem, contraceptive self-efficacy scores go up 0.122 points. Our standardized beta over here, again, this is the same as our correlation value, our R value, and then we have our significance over here. So self-esteem is a significant predictor. The full model is significantly predicting variability in contraceptive self-efficacy. If we were just interested in gender as a predictor, we typically wouldn't do a regression. We would stick with the t-test. We could, in this situation, just look at the correlation between these two things. But if our idea or our basic point in looking at this outcome variable and looking at this set of relationships is to predict those values, we would want to use a regression. And so we can think about how many variables we want in there. Your book talks a little bit about the number of variables that we would want. So you're always giving up some degrees of freedom, the more variables that you're putting into the model. And you might think that let's just throw everything in there. Let's put gender, let's put race, ethnicity, let's put self-esteem, let's put sexual experience, let's put whether or not your mom loves you. Let's just throw it all in there and see if we can predict all of the variability. And so people typically don't want to do that. We want to have often theoretical or conceptual reasons for including the variables that we do include in the model. And we can run the risk of overfitting the model. Often what we're trying to do when we're creating models like this is trying to create a parsimonious model. You'll hear this, this term in statistical techniques sometimes, is that we want to create sort of the best model that fits the data, that is not overfitting it, and is parsimonious as we can try and get it. So as simple as we can make it and as good as we can make it. So we're trying to sort of balance like the predictive power with simplicity here, and being able to interpret these variables. So we've made the decision, we've interpreted the results, we've written that up. For the Module 10 assignment, you'll do the same sort of a thing where you download the data set, answer the research question proposed in the assignment. The research question is, do internalized homonegativity and sexual compulsivity predict internal conflict about condom use? So I'll say a little bit about this outcome variable because it's a favorite of mine. A lot of my research looks at what I've called intrapsychic conflict, so conflict that is internal to you. These items on this particular scale are 3 items that are things like I had a hard time deciding whether or not to use a condom. I feel uncertain about whether or not to use a condom. And so I'm really interested in this particular construct in terms of how much people struggle to try and use a condom or get their partners to use a condom. And so a lot of my work uses this particular variable as an outcome variable. So this is in this same data set. And looking at internalized homonegativity, which we talked about in Module 9, and sexual compulsivity, which we talked about in several of the modules, and looking at those as predictors of difficulty making decisions about whether or not to use a condom. So my thinking behind this particular analysis is that how you feel about yourself as a gay man and how you feel about your sexual behavior may impact how you make decisions about sexual health. So using both of these variables in here is theoretically or conceptually informed. This is sort of this broad sense of what we're looking at. We do know that internalized homonegativity and sexual compulsivity are significantly correlated with one another, but that correlation is fairly small, so we're not going to worry about it because they're not perfectly associated with one another, so they're not completely overlapping variables. And so we'll look at this conflict about condom use. You'll write up a results section and include a table. And in the assignment, I actually provided a table for you in a Word format, which is not perfect and not the way that I love to do it, but I think it's the simplest way without having to upload a million files. So you can just use the table as it is in the Word document, and that's fine. And as always, let me know if you have questions or thoughts or concerns, and post those under the general discussion forum or bring them to a Google Hangouts. All right, thanks.